Hello, everybody. I'm Mohammad Khajanejad from Arizona State University, and I'm going to talk about my joint work with my advisor, Dr. Yang, on simultaneous input and state interval observers for nonlinear systems with full rank direct fit-through. Uh, Safety is critical in cyber-physical systems, which are often susceptible to attacks or unknown inputs or inputs with no known bounds. So input reconstruction and state estimation are important for things like fault detection, attack mitigation, etc. Hence, a motivating question would be, can we simultaneously estimate intervals of states and unknown inputs in such complicated systems? So there has been several interesting work on designing interval observers for different types of systems. However, to best of our knowledge, all of them either consider systems without unknown inputs or do not provide estimates for states and only consider input estimates, or sometimes relatively restrictive assumptions are required. With that in mind, we considered discrete time nonlinear systems with unknown inputs consist of a state equation and an observation equation where X is state, WK and VKs are process and measurement bounded disturbances, U is known input signal, the fit-through matrix H is full column rank, is assumed to be full column rank. F and G are Lipschitz continuous and mixed monotone. I will talk about this mixed monotonicity later. DK stands for the unknown input, could be, for example, attack signals or that are injected into actuators and sensors both. And the most important thing is no prior useful knowledge or assumption or known bounds on the dynamics of decay is available or assumed. So with this, we are interested to design a stable observer that simultaneously finds uniformly bounded intervals of compatible states and unknown inputs. In other words, we want to find so-called correct framers that bound the actual values of our states and unknown inputs. So we use some preliminary tools for this work. The first one is a famous lemma, which says that for an uncertain vector between x underbar and x upper bar and a given fixed known matrix A, then A times x can be bounded from below and above like this. And this bound would be tight. This is a famous lemma in the literature. The other like tools are decomposition functions. So for a mapping F from X in Rn to T in Rm, we call this F mixed monotone if there exists a corresponding decomposition function for this F. We call it FD. This FD is from the higher space of x times x to the same range of t and should satisfy three conditions. The first one is FD of x and x coincides with f of x. FD should be monotonically increasing in its first argument and decreasing in its second argument. So if such an FD can be found for or computed for the mixed monotone mapping F, then it is proven that f of x for an uncertain x is bounded between fd of x underbar and x upper bar and fd of x upper bar and x underbar. So with these tools, our observer consists of two main steps. The first step is state propagation, where we propagate state framers through the composition functions of our vector fields, FDs, to these equations. And the second step would be unknown input estimation, where we find input framers for our unknown inputs that are consistent with the observation equation and the state framers using the observation equation. So how we do that? So we start with the observation equation, And then we have the bounds for our states from the propagation step. From this, we can find the bounds for h times dk using the composition functions of g here and here. And then, given that h is assumed to be full column rank, we can find interval bounds for our unknown input using proposition 1. And choosing this G as the pseudo inverse of J as the pseudo inverse of H. Okay, then we go from here and we say that, okay, we have our first box or bound for decay, this blue box. Also, we know that this HDK should be bounded between our underbar K and our upper bar K, and this is basically this purple parallelotope. So what we do is we find an enclosing box, the tightest enclosing box to this parallelotope, which is this green dotted box. And now we have another box enclosing all the compatible values for our unknown inputs. So then we go and we take the intersection of this green dotted box and this blue box, and we end up with having this red box. So with that, we could prove some interesting properties for our observer. The first one is correctness, which means that the true states and unknown inputs are within the estimated interval, the computed interval. And that is an implication of our main first theorem, which says that if f and g are Lipschitz continuous and mixed monotone, and h is full column rank, and j is chosen as h pseudo inverse, then our observer is correct and the state and input framers are well defined. Then we seek for stability of our observer. So I should mention that the composition functions are not unique, and we could choose any decomposition function for our vector field for this work. But we decided to use the decomposition functions in this reference, introduced in this reference, Yang et al. 2019. And the reason was that we could prove a Lipschitz-like property for these decomposition functions here. And by that, we were able to prove stability or derive sufficient conditions for stability of our observer or uniformly boundedness of our interval with sequences. So we derived three different sufficient conditions in terms of linear matrix inequalities, and one of them is a norm-like equation. If either of them hold, then our observer is stable. On top of that, we showed that if either of the sufficient condition holds, that then we are able to actually compute an upper bound for the interval widths. And moreover, we showed that if condition 1 holds with strict inequality, then we are able to find a uniformly bounded and convergent upper sequence for the whole sequence of the interval width. So with this result, we applied our observer on a benchmark nonlinear system with two states and two output equations and these parameters. So we showed that for this example, the first condition, sufficient condition, holds with strict inequality. So we expect uniformly bounded errors and convergent upper bounds, and hence correct framers. And simulation results actually shows that the actual values of the states and unknown inputs, the green plots, are within the upper and lower framers, the red upper floor framers and the blue lower framers, both for state and known inputs. And as for errors, you can see that the actual errors, the blue plots, are upper bounded with the interval estimate width, the red plots, and they are both upper bounded with the computed upper bound like sequence which is a convergent and uniformly bounded sequence, both for states and unknown inputs. So with that, I'm going to conclude that we proposed interval valued state and input observers for Lipschitz monotone, mixed monotone and linear systems with full rank fit through. We provided sufficient conditions for correctness of the observer. We derived several sufficient conditions for stability of the observer. And we found closed form expressions for upper bounds and conditions for the uniform boundedness and convergence. And in future, we are interested to relax the full column rank assumptions of age and find tighter decomposition functions, as well as necessary conditions for existence and stability of the observer. And we like to add update or refinement steps to our observer. And here is a list of some of the references that have been used for this work. And for this, I'm going to thank you all, and I'm happy to take any questions you may have.